All right, welcome. Today, we're diving into a core engineering principle that honestly keeps every single elevator ride safe. It's called static load. It's this massive, constant force, and for any designer, mastering it is absolutely critical.
I mean, really think about it for a second. Every time you step into an elevator, you are trusting a system that's locked in a never-ending battle with gravity. So let's take a closer look at that battle and see how engineers make sure that gravity never ever wins.
To really get what's going on, we first need to understand the main opponent in this fight. It's a concept called static load, and it is the foundation for, well, everything else we're going to talk about.
Okay, so just picture an elevator, sitting perfectly still on your floor, doors wide open. Static load is the total combined weight of that entire system, just pressing down on the motor's most critical parts. It's a force that has to be supported 24/7, whether the elevator is moving or not. It never goes away.
And what's wild is what actually makes up this load. It's not just the car you're in. We're talking the weight of the cabin, plus the weight of all the passengers it's rated for, plus the massive counterweight, plus all those heavy steel cables stretching up through the building, and even the big pulley, the sheave at the top. You add all of that together, and you get one colossal, continuous force.
So the big question is, how do you manage a force that huge? Well, for decades, the classic solution has been the geared system. Let's break down how this really clever design works.
The whole secret to this design is that the motor doesn't take the full hit directly. No way. Instead, all that force gets routed through a gearbox first. You can think of the gearbox as this powerful middleman, stepping in to absorb the load and protect the motor.
You can actually follow the journey of that force right here. It starts at the sheave, then travels into the gearbox. Now, inside the gearbox, a special worm gear mechanism kicks in to absorb and redirect that force. It's only after all that the now managed force gets passed safely along to the building itself. It's a beautiful, multi-step process of distribution.
But of course, technology never stands still. And today, there's a more modern, more direct approach. Let's check out the gearless system, which takes a completely different philosophical approach to handling that very same static load.
In this setup, forget about the middleman. The gearbox is gone. Here, the pulley and the motor's main axle are basically one solid integrated piece. What that means is that the motor structure has to be an absolute beast, engineered from the ground up to be strong enough to support the entire system's weight all by itself.
And you can see how much more direct this path is. The force hits the sheave, and bam, it goes straight onto the motor's main axis. The only thing standing between that immense force and total failure are these incredibly robust, heavy-duty bearings inside the motor. They are designed specifically for this kind of stress, and they're the last line of defense before the load is passed to the foundation.
Okay, so we've got two very different ways to solve the exact same problem. One is all about distributing the force, and the other is about withstanding it directly. Let's put them head to head.
This really lays out the core difference in philosophy, doesn't it? The geared system uses clever mechanical advantage to spread the load out. The gearless system, on the other hand, relies on pure, raw material strength to just absorb that force head-on.
Now, this is where we get into the really critical details. Take a look at the load type on axis row. A geared system mostly has to deal with radial force. You can think of that as a sideways pull. But a gearless system, it gets hammered by a heavy combined force. That's both the sideways radial force and an axial force, which pushes along the length of the axis. This demands way more robust bearings to prevent a catastrophic failure, like the axis itself actually bending. So why are we getting so deep into the weeds with bearings and load paths? Because this is not just some engineering puzzle on a whiteboard. Getting this wrong has very real, very serious consequences for an elevator's performance and, most importantly, for its safety.
If you have a poorly designed geared system, that whole mechanical chain starts to fall apart. You can end up with damaged gears, which creates a ton of friction and wear. Then come the vibrations and noise. And eventually, the bearings fail. The whole system just becomes unstable.
Now, with a gearless system, you could argue the stakes are even higher. Because the load is so direct, a single point of failure, like an axis that isn't strong enough or a badly designed bearing, can be catastrophic. I mean, the main axis could literally bend, causing the bearings to fail almost instantly and compromising the entire drive.
So ultimately, what this all comes down to is expertise. This quote from Novin Pooya Lift really hits the nail on the head. It's a deep understanding of these forces that lets professionals choose the right system for each specific project. And that knowledge is what guarantees a safe, stable, and reliable elevator for years and years.
So hopefully, after this, you'll never look at that simple metal box the same way again. It's not just a ride, it is a masterclass in engineering, constantly managing these huge invisible forces with incredible precision and strength. It's a silent, powerful system working perfectly just to keep you safe.